Okay, so today I want you guys to kind of relax. This is a little bit of a, what do I want to say, a little walk through several thermodynamic properties that we can measure. Um, this is mostly for information purposes. So this isn't like a skill or anything that I'm trying to teach today. It's just kind of a walkthrough of the interesting things that we calculate with the equation of state. So that's one of the main points today, is to talk about an equation of state. The equation of state, it does just that. It's an equation that tells you what state the matter is in, like solid, liquid, gas, which would be the phase of the matter, but also how much energy it has, how much energy it can contain, and those kinds of things. So that's what we're talking about today. So this is about state functions and physical properties of substances. So let's talk about this state function manipulations, and we'll compare this using this idea of differentiation. So equations of state, it's an equation that tells you about the state of the matter that you're dealing with, and you can look at changes of those states, and there are differentiations that are exact and inexact. And so let's whenever I was taught this course, most of the course, like we'd probably spend a week on just this slide, like taking derivatives and partial derivatives of the equation of state and so on. And then at the end, I really didn't know how to apply any of it. So I teach this course completely different than what you're going to get at other universities. We talk about this a little bit, but we don't emphasize it as much. My course was really like Cal 3 or Cal 4. It was just nothing but calculus. And when I got out, I really didn't know how to make measurements, thermodynamic measurements, or compute any of those things. And so we've already sort of hit this one. Q and W, work and heat, are not state functions. They're pathways or ways that energy is exchanged. And we talked about the stairs. So let's say heat is taking the stairs and work is doing the elevator. And how I get to the second floor in terms of my energy doesn't matter, but how I get there matters, whether heat is lost or gained, or different ratios of heat and work. And so when we say that something is not a state function, we mean that it's path dependent. And when we talk about paths, we're talking about differentiation and integration. So how that path changes from one state to another, that's the derivatives and the integrals. Okay. So the Q and W are inexact differentials. It matters which order you differentiate those. And they cannot be simplified into delta Q and delta W. So it's really not we talk about change in heat, but it's a little bit equivocal. Do you know what I mean by equivocal? You're saying the same word, but you're meaning two different things. So when we say change in heat, we're probably not talking about Q, we're probably talking about enthalpy. And enthalpy is a state function. So enthalpy change is the heat of the reaction. So that word heat can be a bit equivocal. When we're talking about heat of reaction, we're talking about enthalpy, not Q. Okay. Now they're related to each other, so people could argue with me on that. But we don't ever say change in work. We just say work. So we don't have delta W. We just say that much work was done, and that's W. Okay. And their integration is path dependent. Now let's compare that to exact differentials. These are called state functions. And so internal energy, even pressure, volume, temperature, H, those are state functions. And so it doesn't matter how I got to this temperature, this is my temperature. And so I could be at a higher temperature and cool down, or I could be at a low temperature and warm up, but this temperature is a representation of me at this moment in time. And so those are state functions. They define the state of the system. And therefore these changes in all of these are exact differentials, and we'll see what that means just with a simple example here in a bit. And they can be simplified to final minus initial. So whenever you see the deltas, that's great, because you don't have to do a differentiation. You don't have to do an integration. You can just do a final minus initial. So all of those deltas are our friends. When we see a delta, it's just UF minus UI, or VF minus VI. And that's fantastic. And then their integration is not path dependent, and neither is their differentiation. And so the end result of all of this, so we've cut past like 2 weeks of math, and this is the end result. Most integrals can be simplified to final minus initial. That's great. Now let's talk about this idea of exact differentiation and path independence. So here's an example of an exact differentiation and path independence. So here we have, we want to look at this function, the pressure as a function of volume and temperature, and we want to differentiate it in all ways. So what are the ways we can differentiate a formula with two variables? We can differentiate it with each variable, but which one do we choose first? Right? Do we do volume first and then temperature, or do we do temperature first and then volume? And does it matter? Well, if it's an exact differential, it doesn't matter. So that's this conclusion we're going to show here. And what is this PVT? That is an equation of state. So if I give you the volume and the temperature, you can tell me what the pressure is. Okay, so it's telling you what state the matter is in. Given two variables, you get the third. You can calculate that. So there's a function out there, the equation of state, and we would use the ideal gas law. But that's not the only one. That's just an ideal gas law. You could have a more complicated equation of state that takes into account the attractions of the molecules to each other, maybe their repulsions too. So the properties of the material are in the equation of state. And that's what most engineers are concerned about, getting an equation of state that matches the realistic properties of the system. So does an ideal gas law work for us? Not in all cases. So if you get close to condensation, it doesn't work, okay? But if you've got a gas way above its boiling point, way above its critical points, and we'll talk about what critical points are, then the ideal gas law works really well. So for argon in this room, ideal gas law works great. For water vapor in this room, not so great. So at this volume and this temperature, the pressure of water vapor in this room is less than what it should be, because it's not behaving like an ideal gas, because it's in the liquefaction range. The molecules of water get close to each other and they start to attract each other, and that's not ideal gas behavior. So the ideal gas law fails to some degree for water at room temperature in 1 atmosphere, but it doesn't fail for argon, nitrogen, oxygen. So anyway, let's differentiate this equation of state. What do we have for the equation of state? Of course, we have the ideal gas law. V equals nRT over V. Now, a lot of times we work with molar volumes, okay? So it's molar volume would be like 24 liters per mole. And so we would just have that per mole in there. And so look what happened. The N disappeared. So since volume and number of moles are on opposite sides of the bar there, you can bring it down underneath the Vm. And so this is liters per mole right here whenever you see the little Vm. So that's our equation of state. And so let's differentiate that with respect to volume. Okay, so we're taking the partial derivative of RT over Vm at constant temperature. So that little funny d, since I think that's covered in multivariable calculus. Have y'all seen that before? Instead of a regular d, it looks like it's a d in a windstorm. Okay, that's a partial derivative. And what you're doing is you're saying we're going to take the derivative with respect to v, but we're going to pretend all the other variables are constant. So that's what the little t in the subscript is. So we're just taking the derivative with respect to volume. Volume is there to the minus 1 power. Okay. And so what we're going to do is we're going to take it from, we're going to pull out the minus 1 out front, and then we're going to deprecate or drop the power of that volume by another unit, and so it's now v to the minus 2. You could see this as RT v to the minus 1, and this is minus RT v to the minus 2, right? Just like if you differentiate with respect to x, d by dx, 3x cubed. Okay, the 3 comes out front, multiplied by that 3, so we have 9x squared. See, we went from 3 down to 2. Well, here we went from minus 1 down to minus 2. So we dropped that exponent by 1 unit, and we bring that exponent out front, right? The minus 1 came out front. So that's our differentiation with respect to volume. Now we do temperature. So you see its path. We're showing that this is the path we're doing. We're doing volume first and then temperature. And we do this from the right to left. Just like we were doing with the symmetry things, whenever we have these operators, we typically do them right to left. We do the first collision, then the second collision, then the third. Okay. And so now we differentiate with respect to temperature. So it's just minus RT over Vm squared, because there's just temperature to the first power. We bring down the +1, and now it's temperature to the 0th power, and anything to the 0th power is 1. So that's why temperature disappears. And so our result is minus R over Vm squared. So that's if we chose to do volume first, and then temperature. What if we did it the other way? So let's just show we get the same result. So now we're differentiating with respect to temperature first and then volume. So here we have RT over Vm, differentiate with respect to temperature. All that survives is R over Vm. And now we have R times Vm to the -1. So we're going to pull out that -1 and drop the exponent to minus 2. And you see we get the same result. So our equations of state, this is one of the things that our equations of state have to satisfy too. And so this is showing that we have a good equation of state for the ideal gas. Even it's an equation of state that is also an exact differential. Okay, so the point is, whatever order you do it in, it doesn't matter for an exact differential. So there we go. So that's our conclusion. Now let's talk about important thermodynamic quantities. Now think about all of the properties we have. We've got temperature, that's a property of the system. We have volume, that's a property, and our pressure, atmospheres. Okay, and think about what would happen if we change the temperature. If you change the temperature, the volume is going to change too. If you change the volume, the pressure may change. If you change the volume, the temperature may change. So these, if we change one variable, the other one may change, and that's what we're talking about. These important thermodynamic quantities are properties of our system. Like this one is the volumetric expansion coefficient. And now we're not deriving these, we're just jumping right in, and I'm just showing you the equations for each of them. Okay, we'll compute their values, but we won't derive them. Okay, so this is the change of volume with respect to temperature, and this is one that's really important for material properties, like if it's like a bridge, right? If it warms up and that concrete changes volume, you need to have expansion joints. And if it cools down, they compress, and so that expansion joint should expand without leaving a giant hole in the bridge. And so this is a very important piece for construction. Okay, let's look at the next one, isothermal compressibility. So it's isothermal, so we're saying at constant temperature, if I push on something, how does the volume change? Right? We're used to gases, like a balloon. If you squeeze a balloon, you can put more pressure on the balloon will shrink. If you put it in a vacuum, it will expand. You ever see a bell jar where they put a marshmallow in there? So marshmallow is like a foamy substance, and so you pull the pressure out of the container, and the volume of the marshmallow expands. That's this. This is compressibility. So it's the change of volume with respect to pressure. Then we have the Joule-Thompson coefficient, and this one is really interesting. It accounts for the temperature changes with expansion. So now we're dealing with temperature changes, and this is really important for all of us. In fact, right now it's happening way too efficiently in this room, and it's making us uncomfortable. So this is all about refrigeration. So if we change the pressure of a gas, we can drop the temperature. So typically when we expand a gas, the temperature drops. And when we compress a gas, the temperature goes up. So a compressor, if you run a compressor and you run over there and touch the pipe that's going from the compressor into the tank, it's really warm. I mean, be careful, you can burn yourself. It gets that hot. My compressor has little fins, little heat fins that help sink the heat and get it out into the atmosphere. And then we have the internal pressure. This one's really interesting. It has units of pressure, but you can also multiply the numerator and the denominator by a meter. So it's newtons per meter squared, okay, per mole, okay. But look at this newtons per meter squared. What if I were to, and it's called, internal pressure, so that's what pressure is. But what if I were to multiply both the top and the bottom by a meter? This would equal a Newton meter on top, and that's a joule, okay, joule. And then on bottom, I've got meters cubed per mole. So this is how much energy we have in a certain volume in a substance. And so we use this. This is a good measure for the intermolecular attractions. And I use this one a lot for solvents. So when I blend my solvents and I try to dissolve soils and things off the surface, the soil to go into the solution has to move the solvent molecules away from each other. You pay a penalty, okay, because there's so much energy inside that volume. If I'm trying to expand that volume, I gotta break all those intermolecular attractions. But what if my soil is something that gives back those attractions, or maybe even is more attractive? Then I'm getting something out of it. And so that's where like dissolves like comes from. Polar soils go into polar solvents, nonpolar soils go into nonpolar solvents, because the intermolecular attractions have similar energies. If you have a mismatch in this energy, you won't get mixing, and that's when we get phase separation, or when we get stuff that just won't dissolve, things that precipitate out. So let's look at these in their practical values, what we have in tables. So this volumetric thermal expansion coefficient here is accounting for the volume change with temperature. It's given, at least in our book, the constant is called beta. Some books call it alpha, but this isn't kT to the -1. It's a different beta. So sorry, there's only so many characters or variables that you can use. But let's see what we expect for an ideal gas. So this is the ideal gas, and again we're looking at the volume. So what we're going to do is we're going to differentiate the volume with respect to temperature at constant pressure. So this right here, we find the volume equation, and so then we differentiate that with respect to temperature. Okay, so this is pretty straightforward. We put in volume there. We're looking at temperature. It's temperature to the first power, but over here we have a 1 over volume in front of that operator. And so this is NR over VP. So this is the coefficient that is the volumetric thermal expansion coefficient. Now let's put in the numbers for, say, 1 mole of gas. So for 1 mole of gas at 1 atmosphere and room temperature, we get this coefficient of 0.082 per Kelvin. So how can we understand that? Well, that's also on the scale of up here, these liquids, these other liquids. So 10 to the 4th, it's 820. We'll look at that in a second. But if we look at this one right here, 0.082, that's about 8.2% per Kelvin. So how can we understand that? This is the volumetric expansion as a function of temperature. So it changes 8.2% for every degree for gas. So you raise the temperature in this room by 1 degree, and the volume, if we had a bag around the room, would expand 8%. If we cooled it down a degree, it would shrink 8%. So this is the coefficient that tells you how much it expands or shrinks for every degree Kelvin. And so changing it by a degree Kelvin isn't very much, because we're at 298, right? We're going to 299 or 297, and it only changes about 8% That's for an ideal gas, okay? But that's a lot compared to solids and liquids. So look at this table. This is out of the Atkins book, and I don't like the way it's written because it has that 10 to the 6th beta, okay? So that makes it seem like, let's just pick this one, 24.8. It makes it seem like it's 24.8 times 10 to the 6th, doesn't it? Like if you were to take this table and write out that number, you'd be way off. Because the way you should read this table is that that number in the table is, it's saying that 10 to the 6th beta is equal to 18.9. And so beta you would solve for by moving the 10 to the 6 over to the other side, by dividing both sides by 10 to the 6. And so it really, beta is equal to 18.9 times 10 to the minus 6. So this caught me when I was first teaching this class, and I'm looking at the table. I was like, this doesn't make sense, right? If an ideal gas only moves 8.2% for every degree Kelvin, how is it that silicon is moving 2 million times per degree Kelvin? No, it's 2.6 parts per million. Only if it has a million liters and you move it by 1 degree, it changes 2 liters out of a million liters. Okay, or out of a million liters, magnesium changes 24 liters. So very, very little change for these solids. This is 100 times more. So liquids move a lot more, but still small compared to a gas. So so these right here, like this one, from a pen. Okay. So like mercury is 18 times 10 to the minus 4 per Kelvin. So there you would need, if you had 10,000 liters of mercury and you moved it a degree, it would only change 18 liters. Or if you had 1,000 liters, which would be a cubic meter, and you changed it by 1 degree, it would move by 1.8 liters. So a very small amount, but still 2 orders of magnitude higher than the solids. And the gas moves, 820 times 10 to the minus 4. So compare this to a gas, 820 times 10 to the minus 4. So you see a whole nother order of magnitude and then some, maybe almost 2 orders of magnitude, because it's 800 compared to 1. So these are the liquids. Water doesn't change very much at all. So here's liquid water, but solid changes a fair bit compared to these other solids. Right? Remember, this is 10 to the minus 4, and these are 10 to the minus 6 over on the other solids. Now this one is very important for dentistry. Why would this be important to dentistry? Yeah, cavity fillings. Why? So think about this. Which one of these would be the best to use to fill your cavity? The lowest one, silicon. Because if you drink something hot, it's only going to go up by 2.6 times 10 to the minus 6. The worst would be zinc, right? It would go 30. It would grow 30 times for every degree Kelvin that you, and between hot and cold, we're moving a fair bit, right? Room temperature is 298, 373 is boiling. So, it's a pretty big range. We wouldn't drink something that's boiling, but we would drink something that's fairly close to boiling. And that would expand. What happens when it expands is pushing on the nerves underneath your tooth. And you're like, whoa. And then what happens when it contracts? Your nerve also reacts. So you drink something cold, ice water. Now you're going from 298 to 273. Those are a lot of kelvins. And so it's moving a fair bit, and your nerve is going to tell you about it. Yeah. So you could probably find some combination of these metals that are an alloy that has a really low volumetric thermal expansion coefficient. Yeah, and that's what you would want for fillings. And you want it to be resistant to acids and bases, and you want it to be non-toxic. So lead fillings are probably out, right? So there's a lot that goes on in the dentistry that you know, at least the material science of dentistry. I don't know that the dentists actually get into that, but that's where these alloys come from. Is they're thinking about their physical properties and their chemical properties and their toxicity, and they're putting it in your mouth, and so it's important. Yeah. Okay, now isothermal compressibility. This is change in volume with respect to pressure. This would be given kappa. It looks like a little K, but that's a Greek character kappa. So let's differentiate volume with respect to pressure at a given temperature. And so we'll take the partial derivative of this ideal gas law, and we get nRT over Vp squared, and that'd be 24.1 bar per bar. If we were to calculate it for atmospheres, we can multiply by the definition of a bar in an atmosphere, and we get 24.4 atmospheres. And you might see that number. Does anybody recognize that number? Yeah, 1 mole of ideal gas at room temperature in atmospheres. I mean, and that's the volume. And so naturally, if you change the pressure by 1 atmosphere, you get 1 more unit of that volume. This is how the volume changes with atmospheres. And then naturally, that's the slope, right? You go to 2 atmospheres, it's going to shrink. You know, you go to 3 atmospheres, it's going to, or, you know, reduce it, and it's going to expand. And so that's the volumetric, the isothermal compressibility, the change in volume with respect to pressure. Once again, we have this table. So this, you know, this is 1.33 times 10 to the minus 6 bar. And that's a good thing because we put pressure on an aluminum pipe, and the volume of that pipe, it doesn't thin out very much at all. You know, it doesn't change its volume. It only changes, 1 part per million. Sodium changes quite a bit. Look at that. Okay. So this is the way that the solids change with respect to pressure. But I would say that the liquids in this case are more important. This is all still 10 to the minus 6. So this is 64 times 10 to the minus 6, 110 times 10 to the minus 6. These numbers are important for construction. Equipment. And ag equipment. Construction and ag. How am I connecting these to construction and ag? Big machinery. What is big machinery using to do the heavy lifting and pushing and stuff? What's critical for those? Yeah. Hydraulics, that's right. I didn't want to just jump right to that word. I wanted you to arrive at it. Hydraulics, because that's what this is. This is hydraulics. What we're doing is we're changing the pressure on that, and we don't want the liquid to change its volume because it's lossy. If I want to push that piston at the other end of this hose and I pump more fluid into that hose, I want it to push the piston efficiently. Well, I'm increasing the pressure on it. So if the fluid shrinks, that's what this is, it's compressibility. If the fluid shrinks, then I'm losing force. I want the force to go to the piston and push the bucket up and down, and I don't want my fluid to be compressible. So the least compressible fluid would be the most efficient hydraulic fluid. So we would engineer, we would not use, like we would, let's pick one, like carbon tetrachloride, 103, whereas C6, that's hexanol. Hexanol would be better. Okay, mercury would be the best, but man, what a mess that would be. It's toxic, but then mercury would be the most efficient hydraulic fluid. Yeah. And so you could put more pressure into mercury and deliver more pressure to the piston to drive more force onto your buckets and things like that. But it'd be easy to detect a leak. You'd see silver liquid squirting out everywhere. Well, I mean, I say that, but what they do now, and we have some of this in our lab, they put fluorescent dyes in these hydraulic fluids. And so if there's just a tiny little leak, you turn the lights out and shine your black light around, and you see bright green and bright yellow and everything, and the fluid, just the tiniest leak is visible. Now let's talk about refrigeration, the Joule-Thompson coefficient in depth. So this is the differentiation of temperature, the state function of temperature, with respect to pressure at constant enthalpy. Now that's a little weird. Our little at constant have been temperature or volume or pressure up to this point. Now we have at constant enthalpy. It's a little strange, but I've got a plot of it in the notes. So again, we can look at delta T's and delta P's if delta P is small. So it's another way of saying the slope is constant over a short range of pressures. And this greatly simplifies the problem. But we have two versions of the Joule-Thompson coefficient. There's also the isothermal Joule-Thompson coefficient. And that one is actually how we measure the Joule-Thompson coefficient. So they're related by the heat capacity at constant pressure. So we'll do one of these little calculations here. And it has units of joules per mole per atmosphere. So we change the atmosphere, how many joules per mole come into or go out of the system. So it's the change in energy of the system with respect to a change in pressure. And this is a way to kind of show it. We have a high pressure gas coming in. It goes through this frit, this porous barrier, and then we see a temperature drop. We can put the thermocouples in there, and we can see on the outside, after the gas expands into a lower pressure, why does the temperature drop? Well, we had to rip apart the intermolecular attractions, and so they come out colder. And this was always weird as a kid. We didn't have our modern day deodorants. Okay, we didn't have the little stick or the roll-on or anything. It was all spray. It was the popular one at the time was called Right Guard. Okay, it was a deodorant. And so, you're a middle school kid. Your parents are like, man, you need to start using deodorant, right? And so, because the little kids stink. And so then I would spray that under my arm, and it was cold. But the can wasn't cold. Why? Why is it cold? Well, it's cold because of the Joule-Thompson coefficient. So when it sprays out of that nozzle, it's going from a high pressure, 6 or 7 atmospheres or maybe 5 atmospheres into root 1 atmosphere. And the gas, because it's breaking all those intermolecular attractions, the gas is cold, and you're spraying it on an area with lots of nerves, and you're like, ooh, that's cold. So that's why it's cold. The can's not cold. Can's room temperature. So why is it cold when it sprays out? Just because of the Joule-Thompson. So here's the isothermal Joule-Thompson coefficient. So we have this 3D plot. We have enthalpy plotted on the y-axis and temperature and pressure on the x and on the z and x and y. And so this one is the instantaneous slope at constant temperature. You see, we pick constant temperature here along this temperature axis, and this is the instantaneous slope of that surface. So that's this mu t. Okay, that's slope. But if we wanted the constant enthalpy one, we would pick an enthalpy value, and that would trace out this curve that's horizontal on this surface. And then the instantaneous slope of P and T at constant enthalpy would be that slope. And these two lines are related to each other by the heat capacity at constant pressure. So we don't have to worry about trying to figure out how do we keep enthalpy constant. It's real easy to keep temperature constant. So we can measure it with constant temperature and then use CP to get the constant enthalpy value. Okay, so this is how they're related right here when I was saying that they're related by the heat capacity at constant pressure. Okay, so here's an example of measuring the isothermal Joule-Thompson coefficient. So we have a gas flowing at 6 moles per minute. We have a pressure drop of 5 atmospheres, negative 5 atmospheres. And then to maintain the constant temperature, we have 2 thermometers with a little op amp comparator, a comparator that's comparing these two thermocouples, and that comparator is telling us how much heat to turn on. So the heater is being controlled by this circuit that's measuring the two temperatures. And then if we know how much current went through a resistance, we know how much energy we put into the system. So this heater's running at 10 watts to maintain a constant temperature. So what is the mu T? So mu T, we're going to end up with joules per mole per atmosphere. So we got to figure out how that works. Well, 10 watts is 10 joules per second. A watt is a joule per second. Okay, we've got a flow rate of moles. We know that's in the denominator because it's moles. So joules per mole, okay? But this is moles per minute, and seconds and minutes are incompatible. So we got to use 60 seconds per minute to convert the seconds into per minute. And so then we got the per minutes on top and per minutes on bottom. And now we have all the units that we need of the isothermal Joule-Thompson coefficient. So we can calculate that. And that's negative 20 joules per mole per atmosphere. And then we can use the heat capacity at constant pressure, let's say it's 40 joules per mole per Kelvin for this, and we can solve for the Joule-Thompson coefficient. So mu JT is mu T over minus Cp, and we end up with half a Kelvin per atmosphere. So this is conceptually very easy to understand. If I have a 1 atmosphere difference between these two barriers, on the other side of this barrier, then it dropping an atmosphere is going to drop at half a Kelvin. Not very much, probably not a very good refrigerant, okay? But still, it is cooling, and it cools when mu JT is positive. Okay, the mu T is negative. That's showing you lose this much energy per atmosphere, okay, and that drops the temperature. So that's saying that temperature and atmosphere, when it's positive, temperature and atmosphere go the same direction. So when atmosphere drops, temperature drops. So we can have this plot. There's an inversion temperature too, which is a little weird, which we're not showing how that works, but this is how you decide what gas would be a good refrigerant in your car or in your home, and how to get to cryogenic refrigeration. So whenever the Joule-Thompson coefficient is greater than 0, it's cooling, because that says that pressure and temperature go the same way. If I compress the gas, the temperature goes up, and if I drop the pressure, the temperature goes down. So when we have a positive mu, it's cooling. And so we're right around here, 298 Kelvin, and 1 atmosphere. So we're way down here at the bottom. So right here is our room temperature area. And this is saying even at room temperature and 1 atmosphere, nitrogen would be a gas that cools. Now, we don't run our air conditioners on nitrogen gas. We could, but they may not have a very high Joule-Thompson coefficient. So they may not be as good as, say, one of these engineered refrigerants. So they engineer their refrigerants so that they have lots of intermolecular attractions, so that when you expand them, they lose that energy and they cool down a lot. Does that make sense? So we want floppy molecules. Chlorofluorocarbons were really great refrigerants, but they poked holes in the ozone layer. Okay, so we've been engineering them ever since the 70s to try to find non-ozone depleting refrigerants that have a big floppy molecule and has a good Joule-Thompson coefficient. Now, this inversion temperature is when mu goes negative, and that means that temperature and pressure go in opposite directions. So when there's a drop in pressure, the temperature goes up. Now that's weird, okay? But notice it happens at high pressures. So when the gas molecules are really close together, they don't like each other, okay? And so when you drop the pressure, they release energy, because they're relaxing. They're like, we're too close in here. Let me out. And when you let them out, then they release that energy that they had because they were uphill. The way to understand this is this. So this is the cooling region. When molecules are down in this area, cooling. When molecules are up here in this area, heating upon expansion. Right? Because if I've got a molecule that is essentially this distance from the other molecules, it has this energy. To get it to go away from its neighbors, I've got to go uphill, which means I'm gonna have to take in energy from the surroundings, and so I'm gonna cool things down by expanding. But if I'm up here, if my average distance between the molecules is right here, I've got all this extra energy, and so when I expand, I'm gonna release that energy to the surroundings, and I'm gonna heat up. And so that's why I'm not a fan of running hydrogen cars with 9,000 psi tanks of hydrogen, because let's say there's a pinhole in that tank. Look at this. This gray area here is the only place where hydrogen cools when it expands. Every place else, hydrogen heats up when it expands. And if I got a 9,000 psi tank and hydrogen, there's a pinhole, as hydrogen leaves, it heats up, which weakens the pinhole, which makes the leak worse. And so that's bad. There's other reasons too, but that just from the Joule-Thompson coefficient, leaks in hydrogen tanks are bad. Okay, so you'll see me like shoot down the whole hydrogen economy throughout this course quite a bit. Okay, so that's it. And we've used this concept to make our refrigerators. So this is the Lind refrigerator. It's a little weird. We can take this compressor out and we can put a flame here. I'm gonna draw a little flame, okay. And that's how an RV refrigerator works. So we got a propane tank. You know what a propane tank looks like, right? And it just blows my mind that you can burn propane and make ice. That is weird. Think about that conceptually. You're burning propane or any other gas, and yet you're able to cool something down. That doesn't make sense, does it? What you're doing is, instead of the compressor, you're heating up this gas, which makes it expand. So it goes through this little flapper valve, and it ends up in this hot side. And then the heat from the flame is lost to the environment. So it cools down, but it's at higher pressure because it got stuffed in there. And then it expands through this little nozzle, and there's a pressure drop here. And then there's a little flapper valve here that lets the gas get sucked into this compressor. And so we're using the flame to compress the gas. And then the expansion over here inside the fridge or freezer lets the gas cool down and take the heat out of the water and make ice and keep our food cold. But it's really an interesting development. Now, this was one of Einstein's patents, the Einstein refrigerator. There was a Berlin family who they used to make one with ammonia gas, and the ammonia gas leaked out and killed a bunch of people. And so he and Szilard collaborated and made this new Einstein refrigerator, patented in 1930. So that's pretty neat. And so this is their liquid refrigerant Einstein refrigerator. So who knew Einstein worked on relativity and refrigerators?